Good morning. Instead of giving you more tutorials on MATLAB per se, I'm going to introduce new features in MATLAB as we go along solving specific problems. So in this case, I've chosen to develop the solution for assignment number 5. I've also posted the script files and the solutions, printed form of the solutions on Moodle. But I'm also going to go through the thought process and record the thought process of how I would understand the problem and solve the problem and write the script. So we will record develop the MATLAB scripts and functions in a sense live, making mistakes and learning from those mistakes, and hopefully that will be a helpful exercise if you go through it. Now the first problem is called the boundary layers problem, and this is in assignment number 5. And the equations that you see are given here along with the boundary conditions. So the first thing that you have to look at is what is the nature of the equation. So this is y as the dependent variable and x is the independent variable. So y depends on x, and what we want is y as a function of x, a solution that depends on x. And you look at the highest order, it's second order equation. So it is a second order equation. And if you look at the dependent variable y, it appears linearly everywhere. Even though there is x square and then another square, any nonlinearity in the independent variable does not make the problem nonlinear. It is still a linear problem. In order for it to be a nonlinear problem, it must have nonlinearities in the unknowns itself. So d square y dx square is a linear term. And similarly, on the second term, you have only y appearing by itself. P is a constant, and x is a known function. So this is a linear, second order linear ordinary differential equation. So there is hope for getting an analytical solution. And then because it is second order, you need two conditions. And you look at where those conditions are specified. One is specified at y of minus 0.1, that is at x equal to minus 0.1. What should be the value of y? The value of y should be as given here, minus 0.1 divided by square root of p plus 0.01. And similarly at at x equal to plus 0.1, y must equal this value, 0.1 divided by square root of p plus 0.01. So p in this problem will be called a parameter, that it can take any values. So this is typically the extra degree of freedom that you have in formulating a problem. And so you are free to choose, and you will choose depending on other criteria in the physical description of the problem. So here P is going to be a parameter. So the boundary condition also depends on the parameter. The differential equation also depends on the parameter. So the solution must depend on the parameter. Now the questions are, is it a linear or a nonlinear problem? We have already discussed that. We have to look for nonlinearity in the dependent variable, which in this case is y. So there is none. So this is a linear problem. And is this an initial value problem or a boundary value problem? And we've already discussed that as well, because it's a second order equation. We need two conditions. If both the conditions are given at the same independent variable, it will become an initial value problem. But here they are given at x equal to minus 0.1 and x equal to plus 0.1, and that makes it a boundary value problem. Then it says verify that the following analytical solution satisfies the above differential equation. As I said, because it is a linear problem, it is possible to get an analytical solution. And in this case, it is a linear equation, but with what we call a variable coefficient. The coefficients of the y term in the second are varying with position with the independent variable. So often the solutions will turn out to be in terms of an infinite series, but in this case, we are really lucky to get a simple solution like this, y of x equal to x divided by square root of x squared plus p. What the assertion here is that this function will satisfy the given differential equation and boundary condition, and hence it is a solution to that particular equation. If you have that, then there is no need to solve it numerically with BVP4C, but the purpose of this problem is to make sure that BVP4C produces correct results, so that if we know what the correct result is, we can check against that. So the first thing in part C is verify that the analytical solution satisfies this. How do we do that? Well, for example, to check it satisfies the boundary condition, you simply put x equals minus 0.1 in that function, and you will get minus 0.1 in the numerator, which is here, divided by square root of 0.1 squared, which is 0.01 plus p. So it does indeed, by inspection, satisfy the left boundary. And do the same thing with the right boundary. Put x equal to plus 0.1. And you will find that here you have to put plus 0.1, which gives you that term in the numerator there. And then square root of x squared once again, that gives you the 0.01 plus b. So it satisfies both the boundary conditions. How do you check that it satisfies the differential equation? So all you need to do is take the second derivative of this function y of x, plug it in there, and then add it up and see whether they add up to 0. If it does, then it does satisfy the differential equation also. Now, you can do this number of ways. You can take a pencil and paper and start taking the derivatives. You should know from calculus how to take the derivative of a given function. Or you can use a symbolic toolbox that comes with MATLAB, and that's what I'm going to illustrate now. So to start that, all you do is you type something, you start a program called MuPad, which is an interface to the symbolic toolbox in MATLAB. So it'll open up a window like this, and on the right hand side you will see a lot of these symbolic toolbox functions that are built in, and then there are some general math commands related to matrices, solution of differential equations, etc. So it is a toolbox within MATLAB. So you really begin to appreciate the magnitude of MATLAB, such a huge program. So what we want to do is we want to define that function and then take its first derivative and second derivative and then combine it with the differential equation. So I'm going to define y of x as equal to. So this is the syntax that you use to define a function. Colon equal to, and on the right hand side you want to put the actual function that you have, and that is x divided by square root of x squared plus b. Okay, so everything here is treated as a symbol. X is treated as a symbol, p is treated as a symbol as well. Okay, so then it prints out in what is called pretty printing in the textbook style mathematical printing. So it is x divided by square root of x squared plus b. So y of x is now defined as a symbolic expression. MATLAB itself deals mostly with numbers. It's a numerical toolbox. But MuPad is a symbolic toolbox which is derived from another program called Maple, and you might have been using actually this term Mathematica. So it's very similar in function to Mathematica and Maple. In fact, it is a subset of a Maple toolbox for MATLAB. Now I want to take the first derivative. Okay, so how do I do that? I just define a new variable called d1. You can call it anything you want. And there is a function called diff. And I pass y of x to it, and I say take its derivative with respect to x. Okay, so diff takes the derivative of, so it is like MATLAB syntax. Diff is a function that takes two arguments. The first argument is the symbolic expression that I have defined, and I'm saying take its derivative with respect to x. So it takes the derivative analytically and gives me the expression. You can get the idea now. For example, if I want to take the derivative with respect to p, p is another symbol as far as MATLAB is concerned. So if I replace this with p, I will get the derivative with respect to p. We are not interested in that in this particular problem. So then I take the second derivative. So I think you can get the idea. So I have to substitute now d1 here, and I say take its derivative with respect to x. Okay. So I'm taking the derivative of the first derivative. Okay, so I get the second derivative now. So in order to check that this derivative satisfies the differential equation, I want to plug that expression in here and then add that expression and see whether they add up to 0. If they add up to 0, this differential equation is satisfied by that function. So I'm going to say, and there is another function called simplify. So the real challenge in learning all these things is you need to know what are the functions that are available to do a certain task. Okay, so here there is a function called simplify. What does simplify do? It will gather common terms and cancel terms. It's kind of operations that you would normally do on a piece of paper. And I'm going to say d2 plus the second expression. So d2 is the second derivative. So this is the differential equation. Plus 3 times p times y of x. Remember, what's going to happen here is y of x is already defined. So that expression is going to be substituted here, and then the simplification will take place. Divided by p plus x square, close the parenthesis. So that is the second term now, 3py of x divided by p plus x square. And then you need to have one more parenthesis to match with the simplified expression, and you enter, and it says it's 0. It's indeed 0. Okay, so I would accept this as a valid solution in the future if you submit these slides, because you are now learning how to use a more powerful toolbox to deal with symbolic expressions. So that would be considered as a solution, for the third part, that you have verified that the given analytical expression does indeed satisfy the differential equation. Okay, and the fourth part says reformulate the model equation into a system of two first-order equations of the form dy dx equals f1, dy2 dx equals f2. So this is a second-order equation. So maybe I need to open up whiteboard where I can write, and then I will show you how that particular step is done. So let me close the new pad window. So let me open up a new document. Okay, so the question is, how do I convert the second order equation into a set of two first order equations? Okay, so let's see whether we can switch between these two. So as we've seen in the class, the procedure is, it's a second order equation, so you're going to have two first order equations. So you're going to define two variables. y1 is equal to y, and y2 equals its first derivative dy dx. These are the definitions. Then you say, okay, I need to find two equations for these two new variables I have. These equations must always have a first derivative on the left-hand side and some function on the right-hand side, and I need to find out what that function is. So I'm going to simply take the derivative of this one, dy1 dx, which becomes simply as dy dx. But dy dx, by definition, is y2. That is my first function. Okay. Then I need a second equation, and it has to have the first derivative of the second variable dy2 dx. And when I do that on the right hand side, I get d square y dx squared. And this I need to find out from the given equation, which is the expression on the right hand side. I need to move this to the right hand side because d square y dx squared is minus 3py. Okay, so going to be minus 3py, but y is the same as y1 divided by p plus x square. That becomes my f2. That is what the answer is to that part. And of course, you need to find the two conditions in terms of these two new variables. And what you're given is that y at minus 0.1 is this. So, but y is the same as y1. So the boundary condition would be y1 at minus 0.1 is equal to that value that is given, which I don't remember, is minus 0.1. Minus 0.1 divided by square root of p plus 0.01. Similarly, y1 at plus 0.1 is equal to 0.1 divided by square root of p plus 0.01. So now you have two first order equations with two conditions, but these two conditions are given at two different independent locations. That makes it a boundary value problem. And you also have y2. y2 is the derivative of these functions at these two boundaries, but you don't know what they are. Okay, so you have to find that as part of the solution. So the solution to this would mean that you have a domain in the x-axis which goes from minus 0.1 to 0.1, and y1 or y2 Okay, so both are, but what we are really interested in is y1, which is y. y2 is simply its derivative. So it must meet these boundary conditions. So the boundary conditions themselves will change as you change p. For example, when p is 1, you might get a curve like this. Okay, meeting these two boundary conditions that you have here, and this curve satisfying that particular differential equation that you have. Now, this interesting problem, what happens is as you decrease p, the curve may become very sharp like this, okay, with a sharp gradient. That is, y2 becomes very large. y2 is dy dx in the middle zone. So solving them numerically is a challenge, and what really want to do in this particular problem is whether we can capture that using BVP4C. So that is the test. Okay, so let's move on. Use the MATLAB function BVP4C to solve this problem for the following values of p. There are 3 values of p that are given. Plot also the analytical solution on the same graph. Notice how sharp the gradient becomes with the decreasing values of p, I should say there. Such equations are called stiff differential equations or boundary layer equations. All right, so we are given a hint that we need to solve this problem numerically using BVP4C. So let's try to ask for help, BVP4C, and see what the function is about. Okay, so it says that it solve boundary value problem for ODE by collocation method. We really don't know at this stage what a collocation method is, but let's not worry about that and simply focus on what we need to do to get a solution out of this. Okay, so BVP4C is the name of the function, and it takes several input arguments. One is ODE fun, the other one is BC fun, and then the third one is SOLINIT. So that is the initial condition for the solution that you need to provide. So ODE fun is the function that we need to write that will define the problem, and BC fun is the function, another function that we need to write that defines the boundary condition, the residuals in the boundary condition. Then BVP4C will take these two information. So these two functions are very specific to each problem that you solve. So in this assignment, we are going to solve 2 types of problems to learn how we construct that part. And solve is the solution that comes out, that is returned from BVP4C. And solve itself is a structure, and the structure of solve is explained to you here. Okay, solve.solver, it says what kind of solver you use to get the solution. And solve.x gives you the mesh, that is the grid points that MATLAB used to solve for the solution. So it doesn't solve because it is a numerical solution. Unlike NuPad, this one just solves at so-called discrete points. So it just gives you numerical values of the solution, an approximation to the solution, not the real solution. And y is the approximation to yfx, which is y1 in our case, and solve.yp is approximation to y prime, which is y2 in our case, at those collocation points. And there is another variable called solve.stats, which gives you statistics about numerical methods, but we don't have to worry about it right now. All we are focusing on is how to solve it and whether the solution makes sense. And if it doesn't solve, can we understand why it doesn't solve? Those are the focuses in this particular assignment. Okay, so I know that I need to write this BVP function, and I need to write 2 other functions that defines the problem, and I need to pass an initial condition to it. And then I need to plot, because that was asked in the problem statement, that I need to plot the numerical solution as well as the analytical solution for 3 different values of the parameter. So there are some plotting things that we need to put together. Okay, so let's see how I would do that. So I go to my workspace and clear the workspace, clear the command window, and edit a function. I might call it as A5P1, first problem assignment 5. Okay, so I get a blank screen like this in the editor. I have nothing. So I need to, my challenge is to implement that particular problem in a script file. Okay, so I'm going to switch between these problem and the file where I'm going to write the scripts and the functions. So let me just first look at that function that I need to write. Okay, so this is the differential equation. Function equals, you may call it dy, you may call it f, really doesn't matter, equals, let me call it a phi p1 function. Okay, and this function, I guess I need to look at MATLAB again to, let me bring up BVP4C. Okay, so what I'm really going through is the process that you should use to learn more about MATLAB. So I started writing the function, and then I needed to know how many input arguments and in what form the input arguments are required by MATLAB. Okay, so ODE fun evaluates only the f x, y, p. Okay, so that function typically requires you to specify the independent variable and the dependent variable. Let me see where it is described in detail. This is about singular value problems, but and multi-point problems. Oh, here it is right away. ODE fun takes x and y and must return a column vector. Okay, the column vector must contain the functions f of x, y. Okay, so those functions can depend on both the independent variable x and the dependent variable y. Y would be a vector in this particular problem of length 2. Okay, so the real reason I came to here is to see in which order and how many parameters can I pass to this problem. Now I have that, so I can call this as x comma y itself. Okay, then I put a comment here which says that x is the independent variable in the range minus 0.1 to 0.1. I already figured that out by studying the problem. Then I put a comment, y is the dependent variable. Okay, and dy is the functions in the problem. Okay, so I put a blank, so that becomes the comment to describe that particular function. Now my task is to actually program this. So this is the key part of it. So dy, it has to return a column vector. I read that. And it has to return two functions. In general, the length of y will be determined by u. Okay, and I will show you where that is determined later on. But I know in this problem I need to return two values. So the first function we already figured out is y2, and then I hit return. And the second function is the function that goes to the right hand side. So minus 3p y1 minus 3 times p times y1 divided by p plus x square and close parenthesis, and you end that function. Okay, so by putting a return here, I'm automatically creating the second row of that vector. So the first function is y2, and the second function is minus 3p y1 divided by p plus x square. Now you need to worry about, okay, in this function, x and y are sent by BVP4C, because BVP4C is going to call this function. So x and y are defined, and hopefully y1 and y2 will be defined. The length of y will be defined when we make a call to BVP4C. But where does it get p from? So I have no clue at this stage that I'm not passing it. So one way of doing that is to put a global variable p and then pass the values of p as a global variable from the main function that we are going to write still that will call this. So that is the end of this particular function. Then the other function that I need to write is the boundary condition. So I can call it as residual of the BC boundary condition equals a phi p1bc, and I need to know what are the inputs that this function takes. So I need to again go to MATLAB help file and see what does it do. So it says BC fun, the second argument that you see here, takes two arguments, YA and YB. Okay, for column vectors YA and YB. YA and YB are supposed to be column vectors, and YA and YB are the conditions at A and B. In our case, these are the two endpoints, which is at minus 0.1 and 0.1. And YA will contain two elements, Y1 and Y2, because our unknown is of length 2. And similarly, at YB, we'll have YB1 and YB2. And as I said earlier, it's only YA1 and YB1 that we know, the function values we know. We don't know the derivatives. But in some problems, you might have that the derivative is given and not the function. Okay, so you should be able to make those changes and implementations in an exam. And so from our point of view at this stage, we need to have two input arguments, and they are vectors of a certain length, in this case 2, and the A and B refers to the two end conditions or the boundary conditions. So with that understanding, we can now write this as simply YA and YB. And then I need to calculate residual of BC as equal to, remember, wherever I have something on the left-hand side of the function that I'm returning, I must calculate that inside that function. Here I'm calculating dy, which matches with that. Okay, so the boundary conditions are simply YA1 on the left boundary is 0. So I'm taking the first element of YA and say that is your residual, and it's your job to drive it to 0. And then I can put a semicolon to go to the next row and then say YB1. So I'm creating a column vector and end that function. Okay. So I'm not using or specifying, even though YA2 and YB2 come into this, I don't have any specifications on those variables in the problem statement. Okay, so the problem statement only states about the Y, which is Y1, not about Y prime. Y prime is Y2. Okay, so if this boundary condition were changed for Y prime, then you would come and use that boundary condition here, YA2 instead of YA1. So these are the two functions. So we've described our problem. Now our challenge is to make sure that we can use these with BVP4C. So here I'm going to write a function or a script. Well, the other thing I should point out is the boundary conditions here do not depend on P. So I really don't need to pass the global variable P, the parameter, to the second function. So now I need to look at again that function and see the way I'm going to use that is BVP4C, the name of the function, and solve init. Okay, so let me put that and then try to figure out. Okay, so I'm going to call a vector solve, a structure solve. So BVP4C. I'm going to switch between the two, BVP4C, and then the name of the two functions and another structure called solve init, which is the initial condition. Okay, so here I'm going to say it is A5P1 fun. Okay, so it in fact tells me I don't have to kind of switch back and forth. This is the input argument for the function, and I'm writing the next one, the name of the next function. So this is A5P1BC, comma, sol init. Now you can call these variables anything that you want. Okay, the function names, of course, must match with what you are calling them. Okay, and these two functions are not stored in a separate file, they are stored in the same file. So the scope of these functions is just as sub-functions. Only the main function here will know about these functions. If you're calling it from MATLAB, a function called A5P1 fun, it will not know about that. Okay, so now if we ask the question, if we parse this and say, okay, is MATLAB able to understand this? Certainly is able to understand this function and this function, I have an error there. Okay. If you don't have that, it will treat it as a variable. If I didn't have that, it will treat it as a variable and look for the variable definition. Does it have a value? If I put this, it will say, okay, this is a function, so I should look for a function within that particular scope of the file. If not, then go through the search path to find that particular function. So, but I still haven't defined what sol init is. Okay, so let me go and read a little bit about sol init and see what it does. So sol init is created an example here. Okay, is created by another function called BVP_init. So that creates an initial condition. So it has two arguments. Okay, so BVP_init function takes the xinit, the initial grid points that you're providing, and yinit, which is the initial condition on those grid points for every variable that you have, in this case y1 and y2. Okay, so this is in fact where you define for the first time the dimension of the problem to BVP4C. If you put two entries here, it means I have two ordinary differential equations, two first order equations. If I put four entries there, the length of that defines the size of the problem. And this is just a mesh point over the domain. So the minimum one should correspond with the left boundary. The maximum one should correspond with the right boundary. You can have any number of intermediate points because it's only an initial mesh. Okay, this is an initial mesh, and MATLAB will refine it, particularly when there's a sharp gradient. It will automatically put more mesh points there. And we will see what these mesh points are, they mean later on in the course. But from our point of view at this stage, to create this sol init structure, all we need to do is make a call. So in fact, let me copy this and paste it onto my function just before. Okay, so I'm, as I said, I can call this anything I want. I could call it a init if you just like, okay, or you can call it A5P1 init. Okay, let's call that A5P1 init. Okay, so this I need to change. I need to change this to be from minus 0.1 in steps of 0.01 to 0.1. So this is the left boundary. This is the right boundary. And I'm saying divide that into about 20 equal intervals in steps of 0.01. Okay, and this is the initial value over an entire range of x from minus 0.1 to 0.1. Assume y1 to be 1 and assume y2 to be 0. Okay, that's the initial guess that we are giving. So the task for BVP4C is to change these initial guesses to find a solution for us. Okay, so that's how you would construct the solution. And here I think I need to make sure that I put a semicolon so that it doesn't echo print every time that makes the call through these. And that should actually solve the problem. Okay, if there are no errors in there. So let's try and hit the button and see what it says. Most likely I will have an error. Function definitions are not permitted in this context. A5P1M line 4 column 1. Line 4 column 1. I guess I have to have this as a main function. I cannot have a script. Okay, so I'm going to put up a function, and it's not going to produce any output. It's not going to take any input. It just to isolate it as a function so that sub-functions are allowed within that function. So function, and I can give this A5P1. Okay, so, and then I need to put an end, and that creates a cell. Okay, these cells can be collapsed if you notice. Okay, and expanded like that. So that was the error that I had previously. The function definitions are not permitted in this context. Okay, so when I was trying to define a new function, it says, oh, this is a script file, I cannot define that. Now I save this and hopefully it'll run better. Let's go and see. Well, there nothing seemed to have happened. That means it must have executed it, But the reason I don't get anything out is I'm not doing anything with the solution. So if I had, for example, solve equal to this, then it would have returned that solution to the workspace. Then I could investigate whether the solution is right or not. Okay, so now I run that again and I go back, and it did in fact return that solution. Okay, so it is as if I'm calling that function a5p1 without an argument. So it returns a solution in ANS. If I did so LUTION equals a5p1, then it will return the solution into a variable called solutions.struct. And if I do solution dot solver, it will return the first variable that is there. If I say solution dot x, it will return the x values that it used to find the solution. They happen to be the same as the one that I used. Okay, and so here is the solution structure. Another way of looking at it is simply double click on that, and it should open the variable editor. Okay, so it is a structure, and there is your x value, and there is your y value, and yp. Okay, so this is your y1 and that is your y2. Okay, y1 must satisfy the boundary conditions. Okay, now how do I plot this variable? I can go into, let me close this. Plots for solution, no plots available for the current selection. Okay, so this is another way of generating plots. And what it does is if you select a certain variable, then you can plot one against the other. Okay, but because solution is a structure, there is no plot types available for that. So if I say x is equal to solution dot x, then I'm creating a new variable called x. Okay, and then I can say y1 equals solution dot y. All the solutions are stored. Let me just do this. Solution dot y, because I need to know how it stores the solution. So it stores in two rows. The first row is y1, second row is y2. Okay, so I need to take the entire first row and assign it to y1. Solution dot y, and I want the entire first row. Okay, so I would say all columns. Sorry, 1 comma all columns. That is, take the first row, but all columns in that. That is, I'm extracting the solution y1. Okay, so I have here x and y1. Okay, so this is a new feature that you can use to generate a plot. So if you select these two plots, x and y1, you can click here and it says what kind of plots that you can generate, x against y1. You can generate a plot or a bar plot or different types. So let me just select this, and it gives me the plot, but the plot doesn't look anywhere near being right. So obviously there is something wrong. Now, one of the things may be that it did solve because it did not give me any error message, but the numbers are very small. Okay, so there is something in the global variable. Yeah, I did not define that. Okay, so I need to go in here and say global p, and then I need to set the value of p as 0.00. Let me just take the first value that I'm asked to solve, 0.1. Okay, so here I'm declaring p as a global variable and set it to 0.1, and that variable must be picked up here. Okay, and then used here. I'm not sure how it worked because it should have given an error message. So let's try again. Try to solve this, but maybe set up a breakpoint here to make sure that it picks up. it will come, the control will come to this when I execute this function at BVP4C, the control is transferred, and then BVP4C calls these. And so the control must come here at some point. I can see whether the values are coming right. So let me set a breakpoint in both. Okay, so the control has come now. So what is the value of P, 0.1, which is right? And then I can execute that and then look at the values of dy. There are two values there, and it'll then go back to BVP4C, and BVP4C makes a call to the boundary condition. So YA comes with 1, 0, 1, 0. Okay, that's because that's the initial guess I gave, 1, 0 as the initial guess. So if you look at it, the initial guess in fact does not satisfy the boundary condition at the endpoints. Okay, but it is a job of the BVP4C to use that information to drive the residual to 0, which means it will make the boundary condition fit. So it is doing the right thing here. So I can take this out and continue, and then I will see that the answers have come back here, and let me extract those information and try to plot it again. Instead of solution, this time it is in ants. Okay, now if you go back into we did not enter this command at all. Okay, but we automatically, MATLAB generated that command when I went in there and selected those two values, x and y1, and then said plot. So when I do this, it automatically issues that command. Okay, now I get a profile that does match. It doesn't look right either. So obviously I have now a logical error. No syntactical error, but a logical error that I need to figure out. Okay, let's go and look at what might that be. Minus 3py1 divided by p plus x square. Oh, that looks right. We are asked to plot the analytical solution also. Maybe let's just look at how the analytical solution should look like in this particular problem. We are lucky that we have that. So we can plot that and see what should the solution from BVP4C should look like. How do I do that? Because I've been given the analytical expression. So I can go to my main function and create a vector xx is equal to minus 0.1, the steps of 0.01 to 0.1. And then I can create a vector. This is the analytical solution, y as equal to that expression. But I can do this in a single line if I use the element by element operation. So x divided by square root of x dot square, xx dot square plus p. So p is now defined in this, and that will create y, and then I can say plot xx comma yy comma using a symbol plus sign, for example. Okay, so let me just execute that part. So I'm going to set a breakpoint and then step through that. So I've created x, I've created y. Y is now an analytical solution, and then I'm going to plot it. So that's how my plot should look like. Okay, so obviously I have some error in my function that I need to figure out in the numerical solution of it, which is done in line 7. Okay, so let me execute that. And let me try to edit this function to also put, I'm going to put hold on for the graph, and I want to put this numerical solution on the same graph. So I'm going to say plot sol.x comma sol dot y. One comma colon. Okay, so what this is going to do is take the x-axis from the solution and the vector y1. Okay, because this structure has the solution in here, y. Oh, I know what I did. I made a silly mistake in the boundary condition. The boundary condition is not just ya1. The boundary condition should be written as, right now it's driving ya1 and yb1 to 0. But it should actually be the left-hand side minus right-hand side is the residual. So this should actually be ya1. I have minus, but I'm taking it to right-hand side. It should be plus 0.1 divided by square root of p plus 0.01. Okay, and similarly for the second boundary condition, it is yb on the right hand side at plus 0.1. So this is going to be minus 0.01, sorry, 0.1 divided by square root of p plus 0.01. Okay, so that should have been the boundary condition. That was my mistake. Okay, the boundary condition. You can also write this if you like in this form. Okay, so now let's see whether it would run and produce results that look reasonable. So it produces the graph. Let me see how the graph looks. That is the analytical solution for the graph. Now I'm going to continue. I got an error message somewhere. Undefined function on variable p. Okay, I think I know what the problem is. I hope you also do. I put a global in the function, but I also need p in the boundary condition, so I should put global p here as well. Okay, so now I should be able to again step through and look at the graph. So there it is. Okay, so the solid line here is from the analytical solution, and the symbols are from, sorry, the solid line is from the numerical solution, the symbols are from the analytical solution, and the agreement is good. So the next thing that you need to do in this problem is you're asked to solve this for 3 values. So all you need to do is put a loop around it. Okay, and you can do this in one of several ways. What I'm going to do is create a vector called pp, which contains the 3 values of the parameter 0.1, 0.01, 0.00001. And then I'm going to set up a loop for I equals 1 to 3 because I'm doing it for 3, but I can generalize this length of pp, for example. So for as many values of pp, you repeat this every time. And then I'm going to say p is equal to ppi. That is, extract the value of first element when I equal to 1 and put it in p. And that is the one that is passed as a global variable. So what is being passed as a global variable is a scalar. And then and then I need to end this for loop. Okay, so this is going to do for different values of the parameter. And I need to fix up the plot, so I can clean that up by saying I can combine these, for example. Put both of them on the same plot command, okay, and get rid of that plot command. So it says plot both the analytical solution and the numerical solution in one line, and we can, if you like, make this as a red line, okay. And the other thing is to give it a good initial guess, there is a trick that you could do. So, and the hold, I guess I could leave it there without any problem. I could do this one, that is A5P1INIT. Initially, I set that to be equal to this. So I could move this outside the loop. Okay. And then inside the loop, I say it is, if I don't do anything, it will just use the same value because this is defined. And it will, every time it will use the same initial guess, which is 1 and 0. But I have a better initial guess in the solution. So I could take that and set equal to solve. So what this does is takes the solution and puts it as the initial guess. The next time it goes for the next parameter value. And that helps in convergence because you're starting off with a better solution. In this case, this solution, instead of saying it is 1 everywhere, okay, which is what the initial guess was. So this idea is called continuation. You are continuing in a parameter. And so if we are right, I think this should produce the graph and the final solution for the problem. So let's see whether it does. So there you have the red line and the blue dots for the first parameter, but it has come back. Now I is equal to 2 and p will be the next value in that. And so you have the next curve. Okay, and again, this agreement is excellent, exceptional for analytical and numerical one using only 20 points. And do it one more time, and there you have. Okay, so the problem is essentially solved. The way that we have structured it, if you want to get solutions for more values, for example, 0.05, or any number you can put in there, 0.2, and then save that. Because you've generalized it, it'll automatically solve for all those cases. In fact, let's take this out and close that figure and to restart the whole thing and then run it. So there you have the solution for the 5 different values that we put in. Okay, so I think let's stop there.